Have you ever wondered how doctors are able to see what your bones look like after you break your arm? In the late 1950s, an American inventor named Sterling Newberry placed a specimen between an X-ray source and a target plate, giving birth to commercial X-ray imaging. When used on small objects, this is known as X-ray microscopy. So how do the X-rays interact with your sample? The X-rays are essentially being absorbed by heavy elements in your sample. Heavier elements have more electrons than elements like carbon, oxygen, or hydrogen. With more electrons, there's a higher probability that your X-ray will hit an electron, thereby absorbing the X-ray and raising the electron's energy level. As a result, some X-rays pass through your sample and some don't.
There are two different types of X-ray microscopes which produce images in different ways: full-field microscopes and scanning microscopes. The full-field microscope consists of imaging the entire sample at once, while the scanning microscope only images small parts of the sample at a time. The scanning microscope will produce higher resolution because you're imaging a smaller area with a lot of X-rays, but in order to do so, you need to have a low convergence angle, assuming your sample is thick. The scanning type microscope uses a Fresnel lens to focus the incident X-ray beam onto a small point on the sample. This ensures it has a good signal-to-noise ratio thanks to the high count number in a small region.
The full-field microscope, on the other hand, will give you more area to image, but at the cost of resolution. Within full-field microscopes, there are two types: shadow projections and focusing optical element microscopes. With shadow projections, the image is projected from a point source through the object onto the detector. All imaging techniques are ultimately diffraction limited to a maximum resolution of 20 nanometers. However, their maximum resolution is typically the diameter of the X-ray source. In a typical X-ray microscope setup, a synchrotron, an annular particle accelerator, will produce the X-ray beam. The majority of X-ray microscopes use charge-coupled devices, CCD, detectors to record an image. CCD detectors are made up of a pixel grid of X-ray sensitive potential wells. When an X-ray strikes a pixel, its energy is transferred to the material, creating electron flow. The number of electrons is proportional to the energy of the incoming X-rays, and an image is formed from this information.
There is no specific sample preparation that is needed to perform X-ray microscopy. Often for very small samples, such as living cells, the sample is embedded in a polymer medium. This can provide better support to specimen components, and thinner samples can be made easily. Any thickness or size of sample can be analyzed. In X-ray microscopy, the X-rays go through the entire sample, so the interaction volume is the area of the beam striking the sample, moving through the entire sample thickness. Because of this, it has the ability to image the entire sample versus only the surface in optical microscopy. X-ray microscopy is mostly used to image living tissue. No vacuum is needed for X-ray microscopy, so cells can be observed in their hydrated states, often fixed in a block of ice. The interior of samples can be seen where they are opaque to visible light, and allows them to be imaged without being cut into cross-sections.
In addition, X-ray microscopy is best for imaging samples with large contrast and atomic masses. The resolution of X-ray microscopy is 20 nanometers, much better than any other technique for imaging living cells. X-ray microscopy can also be used for producing 3D images of samples by rotating the sample and observing different cross-sections. X-ray microscopy has some limitations. For one, X-ray microscopy has worse resolution than electron imaging techniques. It is also sensitive to atomic number differences, which could distract from other features. Extremely high atomic number materials will block all X-rays from reaching the detector, rendering the technique useless. Also, X-ray microscopes are sensitive to variations in X-ray speed within the sample. Surface features are difficult to see because the X-rays interact with the entire sample.